Hi, this is Subhadeep Chakraborty. I am a PhD scholar at Department of Physical Sciences, ISR Kolkata. I work under the supervision of Professor Shaurin Das. This presentation is about my first project work titled as Volkov Pankratov States in a Quantum Spin-Hall Age. Now, we know that topological quantum matter exhibit a plethora of unconventional phenomena, and amongst them, perhaps the most celebrated one is the bulk boundary correspondence, which tells us that the boundary modes emerge at the interface between topologically distinct bulks. And if we have one Hamiltonian, we can tune its parameters and one can induce a band inversion, resulting in a domain one like configuration of the band gap near the Fermi energy in real space. And when this band gap changes sign sharply, the boundary modes are massless, lying well within the bulk gap. And this is proven by the fact that Jackiw-Rebbi mode exists for a one-day chain. So let me first explain this. So this is our Hamiltonian. You can see this is basically a spin orbit term with a spin polarization along z-axis. If one calculates its eigenvalues, we get E is equal to plus minus h cut phi of kx. So this is our band diagram. So this one is for the spin up and this one is for the spin down. Now let us add a Dirac mass term such that for x less than 0, this minus m term is switched on, this term is 0, and for x greater than 0, this term is switched on, this term is 0, and x equal to 0, there is no mass term. So the band dispersion looks like this. This is the band curvature. This is a eigenvalue equation, and you can see that here the band gap changes sign sharply, so there exists a Jackiw mode just at x is equal to 0. Now in 1985, Volkov and Pankratov demonstrated that when the domain wall smoothly varies in space along with the Jackiw mode, there exists massive subgap states. These states are known as Volkov Pankratov states or VP states. So what he did basically, instead of this taking this sharply varying mass term, he took a smoothly varying mass term mx. Now, a simple model to describe such a system is the BSZ model of AGT quantum well, where one can induce a magnetic gap in the A state or in the bulk, which will result in a band inversion and driving the system into a topological insulator state. Now, why a quantum spin Hall system or topological insulator system is essential for this kind of problem? So, basically, let me first describe what is basically a quantum spin Hall insulator. So, we know that if there is a rectangular type of plate, and if we switch on a magnetic field, then the electrons start moving in a circular path. They are basically localized electrons. They don't carry current, but the electrons which are at the edge, they start moving along the edge, forming skipping orbits, and they carry current. So this is basically known as quantum Hall effect, where the bulk doesn't carry current, but the edge carries current. Now, please note that this is true for a spinless channel. Now, if we have a spinful channel, there exists two spin filtered channel, and these two channels are together are known as helical state. So you can see from the dispersion relation, this is the conduction band, this is the valence band, there is a band gap, and this is basically the surface state or A state. Now these are some uh, work on regarding the Volkov Pankratov states that have been done in the past few years. This is the paper by Molenkamp, where they have experimentally verified the existence of these Volkov Pankratov states in a HGT heterojunction. Also, theoretically, Volkov Pankratov states have been obtained in topological superconductors, well semimetals, and in graphite nanoribbons. Now, how our work is different from theirs? So, in most of the literature, so they have basically varied this bulk band and they have obtained the Volkov Pankratov states in between the varying bulk gap. But what we have done basically, we have fixed this bulk gap and we have added a magnetic field term in the surface state such that we have opened a gap in the surface edge state. So we are expecting to obtain Volkov Pankratov states in between this gap of the surface state. So basically what we have done, we considered a helical state of a quantum spin Hall system subjected to a specially textured magnetic field along the direction of helical state. This magnetic field switches sign at a given point, thereby inducing a mass inversion between the two regions around that point. So obviously, according to prediction of the Volkov Pankratov states, this will generate the bound states, which is basically Volkov Pankratov states, and we show these Volkov Pankratov states have a remarkable characteristic feature when we analyze their spin texture. We also have shown that these bound states or VP states and their pseudopin textures can be manipulated by applying an external electric field. We study the same problem when the magnetic mass gap is finite and show how things can be related to the linearly varying magnetic field case. Finally, our analytical results are put on a firm footing with simulation of a device setup using the Quant package, which is basically a Python-based tool. So first, we assumed a linear type of magnetic field. So this is our S-state Hamiltonian. Here we have opened a magnetic gap of varying of magnitude alpha x. So this is basically our Hamiltonian, and we can perform a unitary rotation to write this in this off diagonal block to write this in terms of the ladder operators. So this is our corresponding ladder operator. Here psi is actually basically a two component spinner. So you can see that if we solve this Dirac equation, we obtain two coupled equation for theta and phi, and upon decoupling, we obtain this type of decoupled equation for theta and phi. Now you can see that these two equations basically look like the harmonic oscillator equations. The only difference being that for the harmonic oscillator, we know that quantization is proportional to n, where n is the quantum state. But here I will show you that here the quantization is basically proportional to root n. So this type of oscillator is known as Dirac oscillator. So one can say that Dirac oscillator is basically a square root of the harmonic oscillator. So now we have applied an electric field having a same similar spatial profile like mx. So here mu x is basically the electric field. So it has the same similar spatial texture linearly varying in space. You can see this minus epsilon x. So if we decouple the equation for theta and phi, we obtain these two decoupled equations, and you can see that this existence of this cross term or term in x is the proof that this is basically a shifted oscillator equation. Now this is the mother Hamiltonian. Now I will compare the results for in absence of electric field and in presence of electric field. Now in presence of electric field, you can see the solution for theta and phi are just basically the harmonic oscillator equation, where this an is basically constant given by this term. Here xi is basically a length scale which determines the localization length of the bound states given by root over of h cut vf by alpha. And from the condition that the index of this Hermite polynomial needs to be an integer, we find that the bound state energy as signal function of n root over of twice alpha h cut vf root n. So this is basically the lambda quantization of graphene, right? Now, when electric field is switched on, so you can see this is basically the equation for theta and phi are basically a shifted oscillator solutions. So here x0 is basically the shift given by this parameter. Now one thing important thing to notice is that we know that for harmonic oscillator, if we switch on the electric field, the shift is just equal for all the states. But you can see, let's first analyze for the zero mode. For zero mode, the en is zero, so basically the zero mode does not shift at all. So zero mode is unaffected by the presence of the electric field. It is topologically protected. And for other non-zero energy states, you can see these x0 is different and they are not similar. So different states with different energy varies differently, shifts differently in presence of electric field. So here this is xi is basically the renormalized length scale. So electric field renormalizes these parameters, and these bound state energies are now given by this term. So this is basically is the electric field basically renormalizes this term also. And one important thing to notice is that there is a critical point at when electric field epsilon becomes the equal to mass gap alpha. You can see the intraspectrum collapses, so there is a topological phase transition. Only zero mode survives, the complete set of vp states vanish. So this is a very interesting result. Now we tend to measure the probability density for each state. So these are basically probability density for zero mode, first, second, and third fifth states. You can see this is just like the harmonic oscillator equations. And when we have applied the electric field, you can see there is clear shift of the peaks of the probability density peaks. So this is a very trivial result. Now we tend to measure the spin texture. So SIN is basically the expectation value of a spin operator with respect to the nth bound state wave functions. So here sigma I basically Pauli matrices. As the wave functions are real, so there is no SY component, there is only SX and SZ component. So we can think like there is of a spin vector which has basically two component Sx and Sz, and they are like rotating in a like 2D projection of block sphere, or we can say they are rotating in a circle. So there is a argument, there is a always angle between the two point of vector, and we can take out this argument, we can derivative along, we can take a derivative of this argument and integrate over the whole space of the helical state. Then one we can measure its winding number in the real space. Now, when we plot this winding in presence of electric field, in absence of electric field, we see that at minus infinity, at the extreme left end of the helical state, the spin is completely up. Then it starts rotating. Then at x is equal to 0, it becomes completely down. Then again it starts rotating, and then again at the extreme right end, at x is equal to plus infinity, it becomes completely up. Similarly, for second bound state, it can be seen that the spin start rotating, it just winds twice times, and then again it becomes up. Similarly, for n is equal to 3, the spin winds just for three times. So one can conclude from this plot is that the index or the quantum number of the bound state carries the information about the topological winding number of the spin vector in real space along the helical state. Now, when we apply this an electric field, you can see there is a clear shift of these winding centers, and as we have increased the electric field, the shift is more and more. This is just because of the fact that this winding center are basically given by the zeros of the Hermite polynomials. You can see from this equation of theta and phi. So, as in presence of electric field, these Hermite polynomials are now shifted. Therefore, the winding centers are now also shifted. Now, for the earlier case, we have assumed this linear type of variation alpha x for magnetic field, where x varies from minus infinity to plus infinity. But this is basically a theoretical concept. This is not something that one should expect from an experimental perspective. So for this reason, we have assumed this kind of model mx is m0 tan h x by L, such that the system size is now from minus L to plus L, and also the gap is finite from plus m0 to minus m0. So this is basically more closer to a realistic view. This is basically more closer to a realistic viewpoint. So if we solve the decoupled equation for theta and phi, these are the two decoupled equations, and here z is basically the parameter tan h x by L. The small is basically m0 L by h cut vf, and lambda is given by this parameter. Now this h cut vf by m0 is basically defines the localization length of the bound state wave function. So you can clearly see that there are basically 12 plus 1 number bound states are present in the system. So this is the basically key difference with the linear case, because in linear case we had infinite sets of infinite set number of VP states, but here the number of VP states present in the system is basically finite, which is equal to 12 plus 1. And you can see that these two equations are just look like the angular momentum equations. Therefore the solutions are given by PL angular, the associated Legendre functions PL lambda z and PL minus 1 lambda z. Now we calculate the overlap between the wave functions of the linear gradient and the hyperbolic gradient case. And the main, I have already told that the main difference between these two systems are this: for linear gradient case, the number of bound states present in the system is infinite, and for the hyperbolic gradient case, it is finite. So as you can see that as we have increased the number of bound states present in the system, the overlap is continuously converging to the one value. Now we have switched on electric field, just having the similar spatial texture of like the magnetic field, which kappa m0 tan h x by L. Here kappa is basically less than equals to 1, because I have already shown that when kappa becomes 1, that means the electric field and magnetic field becomes equal. There is a clear topological phase transition. So if we calculate the bound state energy, this is the expression for the bound state energy. One can see that if kappa is 1, then it completely becomes 0. So the entire state of VP states collapse, and this forms a highly degenerate zero mode. So the recoverable equations are theta given by theta and phi. Here basically pn's are basically the Jacobi polynomials, and these are the some parameters that are used to define these theta and phi solutions. Now let me simply explain this, that if we plot the probability density, so you can see as the black line corresponds to the probability density when there is no electric field, and as we have applied an electric field, you can see there is a clear shift. So this is for the first bound state, this is for the second bound state. Now we tend to measure the detect the VP states in a lattice model simulation. So now we simulate a lattice model of a 2D topological insulator to observe the existence of the VP states by studying transfer properties using Quant package. Quant is a Python-based tool that is designed for quantum transport calculation for lattice model. So what Quant does basically? Quant basically solves a scattering problem. It consists of a finite scattering region and infinite transition leads. So basically, you can see in the diagram, this black region is basically the scattering region. The red region are basically the leads. So Quant basically measures current flow from one lead to another, and it calculates the scattering matrix. And from the lambda-Whittaker relation, this tells us about the differential conductance behavior. So this is our lattice model Hamiltonian. You can see this is the on-site term. This is the standard BSZ theory. This is the on-site term. This is the hopping term along x direction. This is the hopping term along y direction. And we have applied a parametric gradient. This is the mi sigma s, where mi is the value of this magnetic gradient at ith site. And we have applied this electric field epsilon xi minus xc. Now this is the description of our scattering region diagram. So this is the source, this is basically one lead, and this is the drain, this is basically another lead. So we throw one electron from here, and we detect the electron here. So here the yellow region is basically a free edge, there is no gradient here both side, and the shaded region is basically there is a gradient. You can see this gradient varies from a value of minus m0 plus m0. So these are the standard parameters for the HGT quantum well. So upon doing this simulation for this transport simulation, we obtain this. You can see this from this plot, differential conductance plot, that there is a clear signature of these PP states. These peaks are almost one, and when there is an electric field, the peaks are now shifted. As we have increased the electric field, you can see that the shift is continuously towards the zero mode. So what we have done basically, we have verified Volkov Pankratov prediction of presence of VP states using lattice model simulation of a 2D VSZ model. We also have showed that the index of the bound states, or the quantum number of the bound states n, carries the information of the topological winding number of their spin texture in real space along the helical states. So this is the central result of our work. Further, we show that we have the control over the bound states properties and the pseudopin textures when an in-plane electric field is enabled. There is a clear comparison between the electric and magnetic field, and when their magnitude becomes equal, there is a clear topological phase transition and the VP states collapse, and they form a highly degenerate zero mode. Also, there is a finite size correction when hyperbolic magnetic field is applied, and this problem can be mapped to the linear case by increasing the magnetic field strength and the system size. Thank you.